So let's look at silicon carbide. And in general, as a general introduction, it's a material compared to diamond that is readily available in high quality. These are silicon carbide wafers that are manufactured by Cree. And the impetus for the development of silicon carbide as a material has been high power transistors, even LEDs, a variety of device opportunities for silicon carbide in the more traditional, conventional sense. The defects in silicon carbide, because it's silicon and carbon rather than just carbon, 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 offers us some opportunity in spanning a larger range of possible wavelengths, and also gives us opportunities in being sensitive to different atomic locations in the material. And compared to diamond, there are better established processing techniques, because as you see, what we're going to have to do is take the material, and in order to make these amplifiers or these special environments, we're going to have to sculpt out a resonator in the material. And that's actually easier to do in silicon carbide than to do in diamond. So again, by way of introduction, silicon carbide offers a rich variety of what are called polytypes. Different crystalline structures of silicon carbide. Here are some of the most commonly used, but there are a wealth of polytypes. 3C, 4H, 6H. I'm going to be focusing on 4H. And these are determined by the stacking sequence of the tetrahedron, of the silicon carbon tetrahedron. And again, the advantages that we're trying to exploit or take advantage of is that for a given defect, we have the possibility of learning more about the local atomic environment. It is interesting, although in some sense work on this material, certainly compared to diamond, is just beginning, that there have already been a number of spin coherence measurements. That is, taking the defects in silicon carbide, actually in all polytypes, 3C, 6H, 4H, and looking at how long that spin coherence time is and whether you can see that coherence at room temperature. And the answer is positive for a wide variety of polytypes. And again, the opportunity to use these materials to extend the range of wavelengths that we can use. And in particular, if we want to go instead of 630 nanometers, which is in the red, in the visible, perhaps we would like to find defects that emit closer to telecom wavelengths, for example, or push the wavelength out in a particular direction. So I'm going to focus the rest of this talk on a particular defect in silicon carbide. This is a model of the structure, and this is a silicon vacancy. So silicon carbide, rip out silicon, and there are different characteristic sites in just simple 4H silicon carbide. There are two characteristic sites for a simple silicon vacancy, and these are inequivalent lattice sites, and you will see a signature of those two different lattice sites showing up in just a minute. These defects have a net spin 3/2 in the negative charge state. And in terms of these defects, you're probably wondering now, does nature give them to you or do you create them? So nature, and the answer is both. Nature sometimes gives you these defects, which you can find if you just take a piece of material and scan. But for what we want to do, the intention is, can we create the defects we want at the positions we want? And I'll show you that a little bit later. This is a simplified energy diagram for the silicon vacancy in 4H silicon carbide. And if you remember what I told you about what to look for in an electronic structure, here are the critical elements. We have a metastable state here. We have well-defined spin. In this case, it's plus or minus a half, plus or minus 3/2 spin states in the ground state and the excited state. So we have that same kind of structure that allows us to control the spin state and read out information about the spin state. And in fact, as I mentioned, there have been numerous studies already carried out on spin coherence lifetimes in silicon carbide. In this particular one, room temperature control of single spins has been demonstrated for silicon vacancies in 4H silicon carbide. Okay, let's take a look at the optical signature. And this is just photoluminescent spectrum taken at 2 temperatures, room temperature, and 77 Kelvin. So, just a few features. Broad phonon sideband in both spectra, 300 Kelvin and 77 Kelvin. And of course, as we cool the temperature, the relative strengths of the zero phonon line to the broad phonon sideband, the zero phonon line begins to peak out. But for both, the other thing that's important is at 77 Kelvin, we can see, I talked to you, I said there are 2 silicon vacancies at 2 inequivalent sites. So here's V1 at one site, and here's V2, a silicon vacancy at another site. But if you look at these spectra, it's not very impressive. And certainly at room temperature, it's not very impressive, because you can barely see any signature at all. And even at 77 Kelvin, we have these transitions that we want to be our signature for what's happening with the spin state of the silicon vacancy. And the signal to noise isn't particularly good. There is a huge background. So we need to read these spectra with better clarity. And how do we do that? We do that by creating this structure, which I can call, I term an optical amplifier. An optical amplifier is to amplify that photon signal. I call it a resonant optical amplifier, and you'll perhaps understand why I say resonant in a minute. But these blocks indicate a specialized environment that integrates the material and the defect. And these blue arrows say it not only integrates that defect and protects it from the outside environment, which leads to decoherence, all kinds of interactions with electrons and photons. So it's a special preserved environment, but those arrows mean that it's a preserved environment that exercises a degree of interaction and control with the silicon vacancy integrated within, if I can make that resonator, that amplifier, in a particular way. So this optical cavity, this resonator, it's a deliberately engineered structure. The feature sizes are on the order of a wavelength of light in the material. It's an optically isolated environment with discrete photon states. Again, it's optically isolated to preserve the qualities of the defect within. And it is a means of controlling or coupling to the electronic states of the emitter to the cavity. So if this is your first introduction to an optical cavity and you're trying to think of something else that is more commonsensical, then I talk about an analogy with, these are organ pipes. So you all have an association with instruments, wind instruments of different lengths and different openings, that each beautiful instrument gives you a pure tone. And that pure tone is the response, is the resonant response of that instrument. And that resonant response is related to the size and the shape of the instrument. And basically the resonant tones in one way, so this is acoustic, this is not optical, these result from setting up stable standing waves, these are acoustic waves, in the pipes. So here's the schematic. Here's a pipe, here's an organ pipe of a certain length, there's an acoustic wave, and that resonant frequency, that beautiful tone, results when I have a match in the pitch or the frequency of the acoustic wave and the size or geometry of the instrument or the organ pipe. So in a similar way, this is my organ pipe for photons. This is a narrow bridge of silicon carbide. This is 1 micron. So this feature is about 200 nanometers in width. It's several microns in length, and there is a reason for this particular design. It is optically isolated from the substrate. You can't quite clearly see it, but it's a suspension bridge that's held over a substrate. And the most important feature of this nanobridge are the holes. The holes create, in this material, this holes for a photon that's traveling through this bridge. What the photon will see is a periodic variation of index of refraction. The index of refraction of air, which is 1, the index of refraction of silicon carbide, which is about 2.5 or so. And so as the photon travels through this periodically modulated index of refraction, its velocity in a sense changes, it sets up a standing wave. So we create those standing waves and pick out the right frequency of photons traveling through this material by actually making these holes in a particular way to modulate the index of refraction. What does this look like if I actually go further and try to model what it should look like? So these are simulations. It's a technique called finite difference time domain simulations. We're looking top down and side view of this bridge. And what we do is we model the material constants, silicon carbide, air. We change the dimensions of the holes. We change the separation of the holes. And we look at what are the standing wave solutions of photons of different frequencies that are transmitted through this bridge. So what you see in the brightest regions, the yellow to white, are the peaks of the standing waves. Those are the stable solutions. Now, those peaks of the standing waves are where we have extremely high electromagnetic field strength. So at the standing waves, you can imagine these are where the high field strengths are. You can see again, this is, so if you remember this dimension in this direction is about 200 nanometers. These holes are separated from each other, center to center, about 100 nanometers. That gives you an idea of the geometry, and this also gives you an idea that this very high field region is confined to a very small volume. The volumes are typically on the order of the wavelength of light divided by the index of refraction cubed. So for us, the wavelength of light is almost 1 micron. The index of refraction is, let's say, 2.5. That's how small a volume holds this very high electromagnetic field. So it's as if someplace in this room, I have a transmitter, I have a field. Instead of broadband for Wi-Fi, you have a specific frequency beaming down in a very small area. So only when I'm in that area, can I very strongly receive or send information if I use the right frequency. And that's true for the defect. So imagine that I have my defect placed right there, right at the highest field strength of this little nano resonator. When the emitters have the same frequency and are at the right spatial location where I have the highest field, then what the cavity does is it exerts a control over the emitter. Part of the control I'll show you is that's that high field. It starts driving the emission frequency of the emitter, and the end result is that if the emitter is giving photons up more rapidly per unit time, the end result for me in the lab is that I see a higher intensity, a higher flux of photons. So if I were to evaluate this cavity, I want a cavity that actually confines its photons. For me to lose photons from the cavity means that basically it's not very useful as acting as an amplifier, because as soon as the photon goes into the cavity, I lose it. So this low photon loss is something called 1 over Q, and you'll see this parameter again. And very high fields confined to the high volume. So you want a very high electromagnetic field confined in a very small volume, and you want to make sure that this entire amplifier doesn't lose photons, that keeps the photons that come into it. So again, Q over V actually turns out to be the important metric. High Q, that means low loss, confined to a small volume. And this looks like a lot of terms, but we're going to see this again. So let me just briefly go over it. This metric, this high Q over V, we can also express as a Purcell factor, F. And that Purcell factor says that if I put my emitter or defect in exactly the right place in the cavity, and if the cavity has been designed in the correct way to amplify uniquely the frequency of the emitter that I place within it, then what happens is that the emission rate in that cavity actually can be many, many times faster than the emission rate in free space. And this Purcell factor, this enhancement of emission rate, depends on that Q over V, and it also depends on how that emitter, that spatial location of the emitter, where I place it in the cavity, because after all, if the emitter were out here, it wouldn't do me very much good. It wouldn't be a very effective way of having the emitter interact with the cavity. So now we'll go into some of the details. That is what I want out of a good amplifier cavity. This is actually, again, you've seen this again. This is what our cavities look like. If I superimpose where I expect the very high field regions to be overlapping with the cavity, it tells me actually where I want to have the defects. But as I begin to make this cavity, and this is again 1 micron, so clearly this is a cavity that has nanometer or tens of nanometer feature sizes. This cavity has some precision in its design. I need to have the openings of the holes exactly right. I have to have the separation of the holes exactly right. I have to be sure that I don't, in the process of making this cavity, actually introduce defects to the material itself. And unfortunately, many of the tools that I use to make structures like this use particles that have high kinetic energy that actually could compromise the material. So all these questions are, I know what I want to make, I know the design, I know the feature sizes I need to make, Now, how do I make it and assure that the feature sizes are right, the damage to the material is low enough, that I preserve the defects in it so that everything works? So just very quickly to tell you about the fabrication process, I'm not going to talk about the details of this, but Professor Pang and I have both worked all throughout our careers on techniques to make structures at the nanoscale, but without using the tools that most people use to sculpt structures at the nanoscale, but yet to avoid, with the kinetic energy of those tools, to avoid damaging the material. So the way I show you is actually, there are nuances that I'm not going to talk about here. Why we chose a heterostructure. So we chose silicon carbide. We chose a PN structure, P-type silicon carbide, N-type silicon carbide. This is not a transistor. This is not a PN junction. That is not why we chose it. We chose it so we could use a selective, dopant selective, wet chemical etch that allowed us to completely remove part of the silicon carbides so I could get that optical isolation, which is very difficult. Removing this silicon carbide so I have a free-standing bridge is very difficult to do by some of the typical techniques we use in nanoscale structuring. So basically, we mask and write the patterns by e-beam lithography. We do use ion-assisted, high-resolution ion-assisted etches to transfer that pattern into the silicon carbide. Then we use a particular step where we do dopant selective wet chemical etching to remove the N-type silicon carbide. We then introduce the defects into the material. And just to give you a little bit more information about this dopant selective etch process, it's a technique that is light enhanced to drive the process. So it's a photoelectrochemical etch of the N-type silicon carbide selectively with respect to the P-type silicon carbide. And I won't give you more details on that at the moment. Just to show you that actually, and this is to thanks to David Brocker, who was meticulous in not only doing the design, but running the whole range of interacting processes to make these nano beams. That literally when he goes to make his devices, he makes thousands of devices to test, which is good and bad. He makes devices of different geometries, so at any one fabrication run, he has a whole set of nano beams where he can look for defects that are resonant with a wide range of frequencies. His yield is about 80% with a resonant mode, and that is extremely impressive for these structures. And that quality factor I told you, you want low loss, high Qs. These are very good quality factors. They're all routinely about 3,000 to 6,000. We generate the vacancies deliberately by actually after the fabrication, we can either implant carbon ions at various energies, or we implant electron beams. We do electron beam irradiation. This is something we're very much exploring at the moment as well. In terms of, we're also looking at focused ion beam implantation to particularly and specifically create the defects actually right at the part of the cavity where we want the defects to occur.